Hi, I'm Amir Hussein, and I'll be presenting our submission to the Dialect Speech Translation track of IWSLT 2023. When we speak about a dialect, we refer to a variety of a language spoken by a group of people, often in a specific geographic location. A dialect may exhibit differences in lexical choices, pronunciation, and, in case of Arabic, significant grammatical changes across different regions. When processing dialectal speech, we are faced with unique challenges. First of all, its non-standard orthography is rarely written, low resourced, and in case of conversational speech, a lot of disfluencies and incomplete sentences. This is the second year we're participating in the same track. Last year, we mainly focused on cascaded speech translation systems. Highlights of our system include fine-tuning SID and PNSR models, pre-trained on mismatch MSA in a cascaded system. This year, we're mainly focusing on incorporating large pre-trained models to improve both end-to-end and cascaded systems. We also explore combining end-to-end and cascaded systems using minimum base race decoding. In previous year, we also experimented with synthetic Tunisian generated from source model sound in Arabic using bridge-back translation, which showed slight improvement. And we also showed that aggressively normalizing the source Tunisian to reduce the orthographic variations significantly helped for both ASR and MT. In addition to this normalization, this year we are proposing to use pseudo-labeling on the source Tunisian, and to further improve ASR, we include channel matching. This year, the dialectal track consisted of two settings: the constraint setting, in which we are allowed to use the three-way parallel data provided by the organizers. This includes 166 hours of Tunisian Arabic, the corresponding 212K Tunisian transcriptions, and the corresponding English translations. For the unconstrained, we're allowed to use any data. In particular, we used 1,200 hours of modern standard Arabic from broadcast news MGB2 corpus. In addition to that, we used 250 hours of telephony data, and we also used pre-trained large pre-trained MT models such as mBART and NLLB 200. We also switched this year from the conformal block in the encoder, in which the convolutional module and the self-attention modules are stacked on top of each other, to the branch former block, in which the attention module is processing the data in parallel with the convolution module, and then they are both combined. For the ASR component of the cascaded speech translation system, we use the hybrid CPC attention model with the branch former encoder, which provided by ASP.NET Toolkit. We train on condition A using only Tunisian Arabic data. For condition B, we train on modern standard Arabic from MGB2 and the telephone data from Levantine Arabic, and then fine-tune it on condition A. We noticed from the transcription a lot of inconsistencies in words that have the same pronunciation and the same meaning, however they are written slightly different. To mitigate this effect, we propose to use pseudo-labeling, which is basically augmenting the data with the ASR predictions paired with their corresponding speech. We also propose to match the sampling rate, since the target domain is 8 kHz data. And because it's a telephony speech, we propose to add additional telephony data to match the channel. And you can see from the table, from the results, that each of these components has a decremental effect on the word error rate. For the MP component of the cascaded system, for the constraint setting, we are also using the branch former encoder and train on the Tunisian English data. For the unconstrained condition, we're incorporating large pre-trained models like mBART and NLLB 200 and fine-tune them on the Tunisian data. We chose mBART because mainly it was exposed to modern standard Arabic in addition to other languages like French, Italian, and Spanish, which contribute loanwords to Tunisian. For NLLB 200, it was actually, in addition to modern standard Arabic, it was exposed to Tunisian Arabic and other closely related Maghrebi dialects like Moroccan and Maltese. And as expected, we can see that fine-tuning large pre-trained models um, gives significant improvement, especially the NLP, which achieves the best result. From the cascaded results, it can be seen that, as expected, the best results are achieved with the cascaded system, the best ASR pre-trained system, followed by the NLP 200. Our end-to-end speech translation system is based on a multi-decoder architecture, which decomposes the ASR and translation tasks while keeping it end-to-end differentiable. As can be seen here from the figure, the hidden representation from the speech ASR decoder is fed into the MT encoder. And the way this model is trained is with the multitask learning objective, which combines the hybrid CTC attention from ASR and the hybrid CTC attention from the ST tasks. One of the novel things we are introducing here in this system is the integration of the large pre-trained systems, the MT component of the ST system, as can be seen here from the figure, the mBART encoder and the mBART decoder. To combine the systems with different vocabularies, we propose to use minimum base risk decoding on the hypothesis level, which basically selects the best hypothesis from the set using a utility function and the self-confidence, which here encoded as log likelihood p to the p superscript j. We experiment with several variations of the mBART. First, we use the BLEU score mBART, which is basically uses BLEU score as a utility function and log likelihood pj ratios from the model. We also have the unscored mBART, which also uses the BLEU score as a utility function, but the weights are equally likely, they are all equal to 1. And we also experiment with Comet utility function with the mBART. For the system combination, we're combining 5 best systems, the best constrained and unconstrained end-to-end systems, and the best 3 unconstrained cascaded systems. Overall, it can be seen that the end-to-end systems significantly outperform the cascaded systems in the constrained setting, and the transcript normalization always helps, even in the end-to-end system. For the unconstrained setting, the cascaded systems outperform the end-to-end systems, especially the one that has very large models like NLP 200. And finally, the best system combination approach was achieved using Comet mBART. In conclusion, we presented strong dialectal transfer approaches from large pre-trained models to improve both end-to-end and cascaded settings. We showed that pseudo-labeling and channel matching significantly improves the ASR. And finally, the best results were obtained by combining the end-to-end and cascaded systems using minimum base risk decoding, specifically with the Comet utility function. Thank you so much. Looking forward to your questions.